All right, guys, we're going to finish up what we were doing in class today. I'm going to talk a little bit more about absolute value equations, and then we're going to look at a little bit about inequalities so that tomorrow's work makes more sense to you. First of all, you know that the absolute value of x always turns out to be 0 or it's positive. Consider if you take the absolute value, let me consider that without moving that around, sorry. If you take the absolute value of -4, it's +4. If you take the absolute value of 23, it's 23. But if you take the absolute value of 0, it's 0. So absolute value is always positive or 0, meaning it's not negative. So that's where I'm getting the absolute value of x is always greater than or equal to 0. The absolute value of x, as we mentioned in class, represents x's distance from 0 on the number line. Sometimes you'll see people use the absolute value of x minus a to represent x minus a's distance from 0 on the number line, but it can also be interpreted as the distance between x and a on the number line. So we mentioned one like number 1 on the first video, where your job is to isolate the chunk. Let's add 7. Now multiply through by 3 over 2. So 18 times 3 over 2. 2 goes in 18, 9 times 3 is 27. Since 27 is positive, you get your normal case, and your normal case is what we did in class earlier today. So that's where you say that 4x plus 1 is 27 units from 0. That means 4x plus 1 might be at 27 on the number line, or 4x plus 1 might be at negative 27 on the number line. I'm not going to finish this problem. I'm going to remind you that you get two little equations and you then solve out. So ... to finish the problem. Now, what about the others? Well, you do the same thing. The first thing I do is absolute value of 3x minus 5 times the 2 equals 4 minus 18. Isolate the chunk by dividing by 2. Now, if you get a negative number here or a 0, it's an abnormal case. And in abnormal cases, you don't necessarily do the work or as much work. You stop and think through it. So here's what I know. The left side must be either 0 or it must be positive. But the right side is -7. Can 0 ever equal a negative number, or can a positive number ever equal a negative number? No, it can't. So this statement is never true, which leads me to saying there is no solution. If you get something that's always true, you say all real numbers. So let's go to our third scenario. On this one, I'm going to say -7 times my chunk equals 0, which means when I divide by -7, I get 0. So this statement, again, is turning out, because it's 0 right here, it's turning out to be an abnormal problem, which means you don't have all the normal amount of work, and you need to stop and think about it. So I know the only time I can get the absolute value of 0 to be 0, the only time I take the absolute value of a number and get 0 is if I'm taking the absolute value of 0 itself. So for this absolute value to turn out to be 0, I'm saying the inside must be 0. And the difference between this one and the first one is that the first one will have two solutions, and that's normal. This one will have only one solution, so that's abnormal. So your abnormal cases turn out that you either get one solution or no solution at all. So that's just kind of a brief reminder about how to think through absolute value equations, and that'll help you as you transition that absolute value inequalities on tomorrow's video. Now, we did a little bit of this in second block. We did not get to it in first block. So, or fourth block. So I want to mention, remember that if you have greater than or equal to or less than or equal to, it's a closed circle. X is greater than or equal to 2 is shade to the right. If it's just less than or just greater than, it's open circle. X is less than negative 10 is shade to the left. In the next compound inequality, I see that X is sandwiched between negative 2 and 9. Negative 2 is not considered a solution, but 9 is considered a solution. So that's the significance of opening one and closing the other. And then if X is between them, I'm looking at any number that falls in the number line between. So I sandwich or bookend my solution set. Now anytime you have an OR, that's where you have two separate shaded regions. So X is less than or equal to 0, so closed circle, shade left. Or X is greater than 3, so open circle, shade right. So again, that would be two totally different intervals or two totally different shaded regions. Now as far as interval notation, remember brackets go with closed circles, parentheses go with open circles, and you must read it left to right. So in this example, the left bookend is 2, and then the shaded region goes forever and ever and ever rightward, so you approach infinity. Infinity and negative infinity always have parentheses around them. In the second example, the shaded region extends forever to the left to negative infinity, but it's bookended on the right by negative 10. In the third example, the interval's completely bounded. It's completely bookended, so no infinities here. So you're saying the left bookend is negative 2 and the right bookend is 9. Last but not least, the last graph shows two separate shaded regions, so there are two separate intervals. The first shaded region here goes from negative infinity to a bookend at 0. And I don't want to say or. You use or when you do inequalities. You do union when you want to join intervals. The second shaded region starts at 3 on the left and goes forever to the right. So that's just a reminder of how you write interval solutions. So these are the last three examples we're going to do. Basic linear inequalities. The only thing that changes in these versus equations is with inequalities, if you multiply or divide through by a negative number, you've got to flip-flop the inequality. So I'm going to say negative 1/2 x is greater than 12 minus 9. I'm going to multiply everything by a negative 2 so that I get 1x, but since I'm multiplying by a negative, I have to flip-flop the inequality and get negative 6. That means that I would graph it by saying at negative 6 I've got an open circle and I shade to the left. The main reason I'm going over the graphing is just to make sure that you're okay on where the interval solution comes from. On the middle one, it is a compound inequality. Do not disjoin it. I need to subtract 16 from the left, the middle, and the right pieces. So negative 4 minus 16. In the middle, it's 3x plus 16 minus 16, which just isolates 3x. On the right end, it's 1 minus 16. Now I'm going to divide all three parts by 3. So I get negative 20 thirds is less than or equal to x is less than or equal to negative 5. When I divide all three parts by 3. So negative 20 thirds, remember, is like negative 6 2/3. And negative 6 2/3 really sits to the left of negative 5 as I've written it. But remember, I'm going to have negative 20 thirds, closed circle, negative 5, closed circle. And I'm saying that I want all x's that fall between my two bookends. So that means my interval is negative 20 thirds to negative 5. So a lot of times what we'll do is we'll begin to skip over the graphing and shading for these simple inequalities, and you'll go straight to interval solution. On number 3, it's an OR, which indicates that you're going to have two separate inequalities, two separate shaded regions, and two separate intervals. So here I'm going to say negative x is less than negative 5 minus 14, and when I divide by negative 1, I flip over the inequality. Over here I've got negative 3x is greater than 3 minus 6, and when I divide by negative 3, I flip the inequality and get 1. So if I put it in more of a correct order, I would say that means x is to the left of 1 or x is to the right of 19. Now it's in a more readable left to right order, and it makes sense now because if I have 1 and 19 on the number line, shade left of 1, shade right of 19, and as predicted it's two shaded regions, therefore it is two intervals. If you have questions about this, please don't hesitate to ask me Wednesday morning if you want to before school or on Zoom.